Hello, this is Aykut Attar from Hacettepe University. In today's lecture, we are going to work on a very simple model of product variety. So this model is based on Paul Romer's 1990 model, but it is a textbook version, so it will be much simpler than the paper in the model. I, of course, recommend you to check back the original model in the paper as well. And of course, you should read the relevant chapter in the textbook. So let's start. Before I go any further, maybe I can give an overview of the model, especially with respect to the different sectors operating in this framework. So in this model, there will be this household sector. So in the households, they will supply labor and they will accumulate some sort of wealth. So they will hold assets and they will take optimal consumption and saving decisions. So we will have this Euler equation from the household side of the model. And in the production side, we will have three different sectors. One of these sectors is producing the final good. So this is the all-purpose good that is used for consumption purposes and also for research and for the production of the intermediate goods. So there are then these two other sectors. One is producing the intermediate inputs, okay? And the third sector, the research sector, is producing new intermediate inputs. Okay, so they do some R&D, and eventually they end up with new blueprints that is useful for the production of the final good. Okay, importantly, the market structures in these different markets, different sectors differ. Okay, the final goods sector, for instance, will be perfectly competitive, and every firm in that sector will be price takers. The same is true for the research sector, because entrepreneurs, they will be competing with each other to end up with new blueprints. But the intermediate inputs sector, the sector that produces intermediate inputs, there are local monopolists there. Okay, so there is this market power in that sector, and there's positive profit in equilibrium. So those positive profits actually are the thing that incentivize innovation effort. All right, so we will see the mechanics of this in this lecture. So let's start. Okay, so the household sector is quickly summarized in the text, and here I will give an overview. So there's this instantaneous utility function. There are households whose total measure is L. So every single household supply labor, and they have this instantaneous utility function, and they hold some sort of an asset. So they accumulate their wealth optimally, and eventually their behavior is characterized by this Euler equation. So if you want to understand the how you go from this and from an intertemporal optimization problem to this Euler equation, just go back to the earlier lectures, specifically the model on wealth accumulation, to understand that. Now, in this lecture, we are just going to take it as as specified here, the Euler equation, and we are going to build on the demand side of the funds. Okay, so this is the supply side for the asset market, and we're going to build on who is demanding these assets to do what, and what is the technological structure of the economy, so that we understand technological progress and eventually, of course, economic growth. Okay, so the technological structure is slightly more complicated than what you saw before in the, for instance, Solo model or in the AK model. So here, the final good, which is denoted by YT, is produced by means of labor and machines. All right, so there is this interval that we use to measure the machines. So I is an index variable for different product varieties or machines, right? And MT is the total mass or total measure of these intermediate inputs. Okay, now the idea is that if you look at the production function, L is labor and XIT is the total units of machine I used in period T. Okay, I must, of course, I must have told you that this is a continuous time model, by the way. Okay, so, okay, sorry, I went further. Okay, so so these machines are important, but as you also see, the total number of machines or the total measure of machines will also be important. Okay, now if you look at the production function in this way, it looks a little strange. I mean, it is similar to Cobb-Douglas from this point of view, but it is actually, if you think about it a little bit carefully, you will see that it is aggregating. It is a simpler version of what we saw in the solar model. So what do I mean by that? Let me explain. So imagine for the moment a symmetric equilibrium. All right. By symmetry, I mean each and every intermediate input is used in the same amount. All right. As you see here, xit is equal to xt for all I. So the final goods sector is demanding the same unit from each machine. All right. So if you do that, and if you define the total measure of machines in this way, right? So if xit units are used for machine I, and we have machines, distributed over the interval 0, mt, then this would be the total. And under symmetry, we got this, right? Because xt is from each unit, mt is the total mass. So xt times mt gives us the, uppercase xt. Now, if you use this, if you go back to the production function, and if you evaluate this integral, you eventually end up this production function. So this is now the aggregate view of the production relations in the final goods sector, and it is pretty much the Solar model, right? Because right here you have the capital stock. You may imagine that x's are capital, of course, and the exponent is alpha. Mt is the number of machines, but now we find a microeconomic, or more specifically, micro-techno-economic foundation for the productivity of labor, right? So remember the productivity term AT that you saw in the Solar model. Now we understand within such a slightly more complicated technological framework what AT actually is or could be. All right. So that is one important note. Yes. So the takeaway message is this. Yes, this production function is different than what we saw before in the simpler model like Solar model or in the AK model, but it actually creates a sound foundation for what we earlier saw, labor productivity, just AT. Right now we understand what AT actually is in the real world. So that's an important step. Okay, so let's start with the final goods sector. We already discussed the production function. Now try to understand what would a typical firm in that sector do, right? So once again, we normalize the price of this good to unity, because this is now a general equilibrium framework. So I must be a little bit more specific about the market structures and the definitions. So here in this model, we account everything in terms of the final good. All right. So we basically make the price of this to equal to 1 for each instant. All right. So this becomes a numeric of the economy, and this is the profit. All right, profit in the final goods sector for any typical firm. Again, this is a perfectly competitive sector, so you may imagine that there are firms, distributed over the unit interval, for instance, and this is the total revenue. Then this is the cost for labor, right? WT is the wage, L is the total mass of labor employed, and this is the total cost paid for the machines. Okay, remember, if xit is the unit of machines demanded. Now we are defining the price of each machine in this way, PIT. So this is a lowercase p. PIT is the price of machine I in instant t. Okay, so if we sum over all this using the integral term, then we get the total cost. So there are no fixed costs, and this is a pretty simple problem. Now don't get intimidated by the integral terms, because integrals are just summations, right? So you can take first order necessary conditions in a simple way. And these first order conditions give you the inverse demand function for L and the inverse demand function for X. Okay? So that would be key. Why? Because the inverse demand function for the intermediate input x would be taken as given by the local monopolies in the intermediate goods sector, so that they will get the, their profit maximization problem. They will solve the profit maximization problem given the inverse demand. Remember the typical monopoly problem from your undergrad years. So that's the idea. So that equation that you see here, the inverse demand function for the machine xi, will be an important thing for the later slides. Now, of course, you should also be careful that GDP is defined in this way here. Okay, why is that important? Because these are intermediate inputs. So total output minus intermediate inputs must give you the gross domestic product okay, at T. Okay, so now the intermediate input sector. Okay, so this is the sector that creates positive profits in equilibrium, and this is because each machine is, produced by a local monopoly. All right, so that's the market structure that we take as given, and you may imagine that, at the background there is this, patent law that gives the sole production rights to these monopolies. Okay, so pi IT will be the profit for the local monopoly I at period t or time t. So that profit is written in this way. So be careful here. That PIT now is this inverse demand function that we found earlier. And here the total cost is given in terms of the, total production. Why? Because in this model we assume that the intermediate input sector has this one-to-one production technology. All right. So they take the final good as the input, and there is this one-to-one relationship between the input and the output. All right. So this is a, this is the simplest way for such models to operate. It's a simple assumption, but this is not totally unrealistic because it is a fundamental feature of many other models, right? Remember the typical Solow model. In that model, there is this capital accumulation equation, K dot T equals IT minus delta KT, right? So gross investment minus depreciation would give you the total increase in the capital stock. Now, what happens there is that the economy takes final goods and convert it to an investment, right, from YT to IT. So that happens here as well. All right, so you may imagine in this way. Okay, so pi IT, if we substitute for the inverse demand function, it is this, then this is a very simple problem, and you can solve it to find x equal to alpha to the power of 2 divided by 1 minus alpha times L. So let's stop here to understand what does this solution mean. So this is a concave production function. This is linear. So the solution is unique and it is interior. Okay, we assume that the solution is interior because otherwise it is not very meaningful from our practical purposes. Now, what do we see here is that since L is given for, each machine, right? So there's this final goods sector that employs L units of labor. We see that the solution is actually symmetric. And it's also important that if the final goods sector is getting larger and larger, these local monopolies produce larger amounts of intermediate inputs. It makes sense because, they increase each other's productivity, right, in the final goods sector. If you look at the production function here, again, right, so their productivity is dependent on each other's. So we see that. So that's important. L is getting larger. Optimal X produced by the local monopolies is getting larger, and symmetry is also important. I will talk about this in a moment. Okay, well, yeah, here I'm talking about that. So let's summarize some of the results. First, there is symmetry, right, between intermediate inputs and across time as well, because we take population or the labor force as given. So it's a constant number. There's also time invariance. Okay, it's there. Now, growth, so this is a growth model, right? So you want to understand the foundation of economic growth here. So where does this growth coming from? So let's look at GDP for that matter. So if you write GDP in this way, and if you put the definitions, that if you put the results that we found earlier, you realize that GDP is proportional to the number of machines. Okay, so that's the entire point. So population is fixed. So GDP per capita is also proportional to the number of machines. So understanding how the number of machines increase in this economy is entirely about the economic growth. So if you want to understand economic growth, you want to understand how the number of machines would increase in equilibrium under, under a competitive setup. So if you let the markets behave and given, of course, the monopoly power to the intermediate sector, what would happen to MT in the long run, right? So that's the idea, and eventually we're going to understand that an economy is developing here by increasing the number of machines, right? So along the growth path of the economy from you know from some pre-modern stage to the modern stage, we see that there is this number of machines increasing. Okay. And finally, the equilibrium level of profit is important here. Why? Because the research sector will look at the intermediate input sector to understand whether it is optimal or not to do research. Okay, so then we write the profit in this way. So basically, if you put x here and put it back here, right, to find the value function of the monopoly I, you end up end up with this. All right. So good. Now we can talk about the research sector. Now, research sector will be competitive, and there will be free entry. So that's important. So there will be a large number of entrepreneurs. Each one would be trying to find a number of new blueprints for machines. Okay, so this is that m dot t. All right. So this is again a continuous time model. So each instant there is this research effort going on, and that eventually, entrepreneurs eventually end up with this number of new machines. All right. And we assume that these machines, when they are invented, they automatically increase. The final goods sector will start using them automatically. All right, so there's no, institutional or technological barriers there. So that's an important assumption as well, because relaxation of it could imply different things about growth policy, etc. But for now, for the simple model, we assume that new MTs will be used by the final goods sector. Okay, so this is the production technology of research. So this is the, let's say, knowledge production function. So you will hear this phrase in later lectures, or you will see that in some of the textbooks or the articles. So this is a simple knowledge production function. Knowledge, of course, is new machines, because remember the blueprints of them will embed new knowledge, right? New complicated stuff about science and technology and etc. And that depends on two things here. Lambda is some fixed research productivity, and RT is the total units of the final good that is used for research. Okay, so we take a great shortcut here and assume that we only need to spend the money, right? So there's no labor input requirement or some other stuff. We just spend the money. That money, through this pretty abstract knowledge production function, translates into new research. Okay, so that's the thing. Now, using that technology, that competitive research sector will try to find an equilibrium amount of R. Okay, so that's the idea. So how much that sector or how much that entrepreneur should spend on research. So that's the key question. And for this, we must write the net payoff of the entrepreneurs, right? So the net payoff depends on two things, of course. First, the profit stream, right, minus the cost, because there would be some profit if the entrepreneur invents a new machine. He or she will be producing this in the intermediate sectors starting from that point on. Okay, so here prospective entrepreneurs just try to calculate the entire profit stream from that invention. Okay, so how can I do that? How can they do that? Well, this will be given by pi divided by r. Remember what pi is. Pi is that number. Okay, so this is profit flow for any instant, right? And this is r. R is the interest rate in this economy. So what pi divided by r is that this is the unit profit from research in present value terms. Okay, so I will do the research. I will invent a number of machines, and each machine that I became the that I would become the producer of in the, starting from that point on, would give me that profit from that time on until positive infinity. Okay? So how do I write that? Well, there's a proof of it. Let me show you here. So here we assume that these entrepreneurs try to find the present value of this entire profit stream. Okay? And we know that at each instant they will make this profit. Okay? And they will use this discounting term. Now be careful that they are not, subjective, right? So these are market players. So they understand that they should discount the future at the interest rate R. Okay? So that's an important thing. So if you solve this for the entire, horizon, you will get this. Okay, so that's pretty simple. So you can actually work on this. Very simple, integral result. So then each entrepreneur expects this future profit stream in present value terms for each machine they invent. Okay, and what's the total flow of new machines? This is m dot t as we define here. And what is the total cost of research? It is R. Right? R units are spent to invent m dot t new new machines. Okay, so that's the thing. Okay, so this is the thing. This is the net payoff term that these entrepreneurs would try to maximize. Okay, and again, this is with free entry and under perfect competition. So if you replace m dot t with lambda r, this is the payoff now, and this is the formal description of the production function. Now, have you ever seen a linear profit function before? I don't know, but in such models, the free entry eventually forces this to be true, right? So look at that. If this is true for any positive r, it is maximized, right? Now, why cannot be any excess profit in this market? Well, because of free entry. Why not nobody is manipulating the market? Well, because this is perfect competition. So everybody is trying to compete with each other, and everybody takes prices as given, etc., etc. So eventually, the market would settle down at this condition. So this is R equals lambda times 12. This is the zero profit condition, because if there's perfect competition and if there's free entry, then equilibrium condition reduces down to the zero profit condition. Okay, so then that's the zero profit condition. Now this has a special term in the endogenous growth theory. It's called research arbitrage. Okay, research arbitrage equation. So we denote it by RA. Now, as you see, everything actually revolves around the asset market, right? Because households supply funds, and they decide how much to do so and how they can do that through the earlier equation. And then there is this demand side. Entrepreneurs would demand funds for research, and that's the demand condition. All right. And of course, you should be careful with the economic logic behind it. If research is more productive, okay, and if research is more profitable, then there would be, of course, a larger demand for funds. So R is larger. Okay, so that's the idea. Now these two conditions now solve the model for R and G. That's basically because G now is endogenous. How do I know G's? What is G in this model? Well, G will be, okay, where is that? All right, here. Now, imagine that if consumption possibilities will grow at the rate G, then production possibilities would also grow at the same rate, right? So for that reason, the growth rate of GDP, which is basically pinned down by the growth rate of M, is actually equal to G, all right, in that model. So M dot divided by M, I think I missed that too. I missed to write that explicitly, but G must be equal to M dot divided by M, all right, by definition, right? So, okay, so these two conditions then, so here I draw a figure, so this is the earlier equation, right? This is that, so if you recall the earlier equation, so this is that, G as a positive, positively sloped linear function. So it is that, and this is the research arbitrage condition, right? So once they intersect, they determine the equilibrium growth rate G. All right, so that's it. That's it. So if you solve it explicitly, you will get that. All right. So what do we learn from this? Now remember the wealth accumulation model that we studied earlier, right? There is this budget constraint, and households take R as given, and they determine how much to consume and how much to save. But those decisions would be taken R as given. Now we look at the technological side of a similar dynamic general equilibrium model, and we understand that R must be depending on the research productivity in the economy and what is the unit profit by producing the intermediate input. Okay, so if we get this together, we understand that growth rate of the economy. So this is the growth rate of GDP per capita and GDP as well, because labor is constant here. So growth rate depends positively on research productivity. It has this wild expression depending on lambda, and also positively depending on L. So later on, in a couple of weeks later, we're going to discuss the scale effect problem. It's basically here, all right? But for now, we just put a brief remark about that. Okay? So that's it. That's the very simple formulation of an endogenous growth model where people are deliberately, purposefully choosing research for profit motive, but at the end, that would create a growth. Okay, that would create secular growth of GDP per capita. So that's the idea of endogenous growth. So the most innovative aspect of this model by Paul Romer, published in 1990, is that for the first time we start understanding that so there could be a general equilibrium economy, and in that economy there could be one sector that is not competitive, and eventually purposeful innovative activity would result in growth. And then through this slightly more complicated setup than the Solos model or the Ramsey model, we understand what explains growth. Okay, so here look at the growth rate. So it depends on preference parameter and it depends on technology parameters as well. So this is the idea of the entire neoclassical paradigm, right? So there's endowments. Here the endowment is labor, for instance, and there are the set of technologies. So here technological parameters are there, and there's of course preferences. So the entire outcome must depend on such things, right? And of course, people interact, firms interact, different sectors interact, and sometimes government also intervenes. But eventually, the most important outcome in the model, which is G here, depends on all these three: preference parameters, technology parameters, and the endowment of the economy. So, again, this is the simple version. So you should check the textbook and you should check the original paper itself to understand more about the foundations of economic growth depending on the accumulation of machines. Thanks for watching.